We are here to address the problem of reusing needle injection equipment and accidental needle stick injuries that contribute to a variety of blood transmitted viruses such as HIV and HBV. The WHO has confirmed that 40% of the 16 billion injections that were given with reused injection equipment led to 21 million new cases of HBV and around 260,000 cases of HIV. Now, these viral infections could have been easily mitigated if needle syringes were absent in the first place.
Our solution to preventing blood-transmitted diseases is disposable needleless injection cartridges. Our cartridges are sealed during manufacturing to prevent reuse, and they don't contain the needles, so there's no chance of accidental needle stick injuries. In addition, we've also reduced the risk of surface-to-surface transmissions by automatically ejecting the cartridges each time into a biohazard container, and then, to speed up the rate of vaccination, we'll be able to chamber a new cartridge from a magazine. As you see here, a cartridge is made up of two parts. We use a compressible fluid and an incompressible fluid because, according to research by Professor Mitra Gotri, Department of Chemical Engineering at UC Santa Barbara, fluid jets creates a reservoir within the skin which impedes the stream unless a tremendous amount of force is used. The cutting fluid, a gas, will be compressed by a linear hammer to act as the cutting element. Once the cutting is complete, an incision will decompress. Afterwards, compression springs will pull the hammer until the suspended medication has been injected. The incompressible fluid will keep the cutting hole open so that all the medication goes in. The reason our hammer has a lower velocity when injecting the medication than compared to the cutting fluid is because we want to reduce molecular shearing. Annalise will explain why we need to reduce molecular shearing.
When the complex molecules in our device are injected, there is a chance that the molecules will shear during this process. We want to limit shearing because shearing is similar to the denaturing of a protein. When a protein denatures, it will reverse its structure from tertiary to secondary to primary structure, leaving just a polypeptide chain of amino acids. The primary structure of the protein does not perform any function, meaning it would be useless in cell processes. Similarly, the shearing of the molecules being injected will cause them to become deformed and dysfunctional, like the denaturing of a protein. Without the molecules carrying out their proper function in the body, once injected, the desired effect of the medicine injected will no longer occur, which will defeat the purpose of our device if the medicine were to no longer work properly. To fix this issue, we will be using a specific type of hydrogel called nanogels, which have properties to protect against shearing, like good biocompatibility, high stability, and high functional flexibility. Raziel will go into more detail on nanogels and its incorporation in the medicine being injected.
According to Nicholas A. Pepes, a chemical and biomedical engineer specializing in drug delivery, hydrogels are three-dimensional networks of polymers containing hydrophilic groups cross-linked by hydrogen bonds, van der Waals forces, or other interactions to absorb and retain a substantial amount of fluid without undergoing dissolution, with nanogels being hydrogels with a size anywhere between 1 and 1,000 nanometers. As Annalise stated earlier, nanogels are used to reduce adverse drug reactions by preventing shearing. So, how can we load the drugs into these protective nanogels? Our primary method is through a storage structure in which drug molecules are concentrated in the inner layer, with the outer layer being the gel film, while the other options being the uniform dispersion of drug molecules through the nanogel and binding molecules to the gel via covalent interactions. Alongside molecule protection, nanogels regulate the process of drug release in three ways, including gel degradation, gel expansion, drug diffusion, and the breakage of interactions between drug and the nanogel. Zain will further explain the application of this technology in real life.
For the injection site, we are choosing the intramuscular route where most modern injections go. Although this may differ for younger age groups, we are also offering injections from under 1 milliliter because most vaccine doses today are under 1 milliliter when distributed through normal systems. We also took into account pressure injuries in our system caused by high pressure, water jets damaging tissue, and depositing bacteria. We have accounted for this risk by using jets with extremely small diameters to minimize cell damage. Our solution also enables mass vaccination campaigns because it allows for the sterile administration of dozens of vaccines due to its reloadable magazine without the need for sharps or needles. Instead of a team of medical workers, just one or two can mass vaccinate a community against diseases like polio or the coronavirus.